Thank you, Alan. And we're all used to this. The daguerreotype is all about problem solving, so it's not changing a room around 190 degrees is nothing. It's a pleasure for me to be here. It's a pleasure for me to see such wonderful work exhibited here. I thank Alan for organizing it. It's a labor of love, as is the daguerreotype. I'd like to thank everyone here at the Center for Alternative Photography, Jeffrey, Eric, Christine, for really working together to make such a wonderful thing happen. When Alan asked me to talk, he said, Mike, we would like to have you talk. And I said, okay, I thought I would talk about, I forget what I was going to talk about, but he said, no, people want to know how you do things. And I thought, well, I don't know. So I thought, gave it some thought, I thought, I'd make it a bit mysterious. I'm going to call it the colors of the daguerreotype. And this talk is really based on my ongoing research for my PhD dissertation. The working title is The Techniques and Material Aesthetics of the Daguerreotype. And the overriding question is, what were the materials and methods used by 19th century Daguerrean artists to produce their finest work? So the first color I want to talk about is the color of silver iodide. Silver iodide, iodine was discovered as an element in 1811, and soon after people were working and trying to discover how salts of silver respond to light. Silver chloride responds to light, silver bromide responds to light, silver iodide responds to light. And it was the chemicals that started the drive towards photography. So this is an illustration of William Henry Fox Talbot's iodine rings. Fox Talbot published in the Athenaeum just less than 2 weeks after the announcement of Daguerre's process what he had discovered about silver iodide. And if you take a crystal of iodine and you put it on a silver plate, the iodine will react with the silver and create radiating rings of color. Those that do Becquerel know the concept of first, second, third cycle colors. And so what we have here is the rings, and the outermost ring is first cycle, and it's going through the spectrum. But what you can really learn from this is if you cover half of that ring with an opaque card and just let it stand under a lamp or in light for 10 minutes or so, it will darken. The iodine will respond to light, no mercury required. What you get, if you'll notice, is what everyone else in 1835 noticed, in 1825 noticed. Where there's light, you get dark. So you get the reverse, you get a negative image. And this was the real challenge. How do you make light white? So a couple things to see about this plate in particular. You'll notice that the fastest coating and the densest silver printout is in the first cycle magenta. It's really astonishing to notice that in the blue region there's absolutely no response to light, which is a revelation for me. So if you put the plate in the camera with just iodine and just uncap the lens and wait for 20 minutes, you're going to get the opposite. Where there's light, you get dark. This is an experiment when I was replicating Joseph Saxton's early work. No polish at all on this plate, by the way. This is before they even knew about how to polish. Just rubbing the plate with nitric acid, give it iodine, put it in a cigar box, and expose for 20 minutes. And where you have light, you get dark. So the real hero of photography is Daguerre. He's the guy that was able to establish how to get where there's light, white. So if you put a simple drop of mercury on a silver plate, you will get the most astonishing amalgamation of brilliant white crystals. Doesn't matter if there's iodine on the plate or if it's bare silver, you're going to get this amazing crystalline white deposit. Now I have to understand that Daguerre must have observed this, or any scientist would have observed this in 1814, well before photography. But where Daguerre has an advantage is that he's also working with the concept of direct positive images. You know, he advanced Niepce's work with the bitumen of Judea, which gave us sort of an asphalty type tone as a positive, advancing it into the phototype, which is the distillation of lavender, but developed with the fumes of kerosene to clarify the shadows so you have a white direct positive image. So Daguerre has the advantage. He understands that silver iodide is light sensitive. He understands he wants white. This is not a broken thermometer in a chemical cupboard. This is knowing that silver mercury amalgam gives a white image and knowing how to use vapors to control development. And so a drop of mercury is too far. It will totally obliterate. You can't wipe a plate with mercury and try to develop an image. It's going to be totally obliterated. But holding back on the mercury reaction with the vapors of mercury, you start to get an image. So by 1837, Daguerre has figured it out. And if you read his manual, you'll find a clue. What's the best silver iodide to use? So what he writes is, it should be left until the surface of the silver has turned a bright golden yellow color. If left too long, the bright yellow will turn to violet, which should be avoided because the light will not have such a powerful effect. On the other hand, if the yellow were not sufficiently bright, the image would be much more difficult to obtain. Judging the correct color has always been a matter of viewing conditions and interpretation. You tell me, coat to a strong yellow, what the heck does that mean? Right? If you're looking at the plate with a candle, that's a different yellow appearance than if you're looking at it under a fluorescent light or daylight. Even the angle of inspection will affect your interpretation of the image color. So what I needed to do was come up with some sort of way of standardizing this, and I apologize for the color on the plate here. What this is 4 different levels of iodine on a plate, 10, 20, 40, and 80 seconds of iodine exposed in the camera, developed with mercury vapor. What really astonished me was the very, very thin coatings actually gave me a very foggy image with very foggy plate with no image detail. That was new information to me. But the strong yellow wasn't indeed the best photographic image, and when it got into the violet, we lost some speed and contrast. If you take the step further, when you add the bromine to the mix, you extend the spectral sensitivity, and what you'll notice in this plate is, yes, still the light yellow gives you a lousy image. In fact, none at all. However, the magenta coating, this is a multiply sensitized plate, again, 4 variations of iodine. How do we accurately describe this color? Is it rose? Is it red? Is it pink? Your call is as good as mine. This is why you can't read a 19th century manual on what the proper color should be, because you're going to get 19 different opinions. But in any case, I'm going to call it magenta, for lack of any standard. So this magenta coating has given the brightest, whitest, fastest response to light. As you move it to the violet range, you can see in the upper left target, it's now lost a bit of speed and a little bit of contrast, but it's warmed up in tone a bit. And then if you take it to the full blue coating, further speed is lost and further contrast is lost. So this would be my working ideal sweet spot. This is the magenta. Now, I have to say, I'm looking at this plate. What I believe now is this is the color that you want to present to the scene. So, if you're looking at iodine and then bromine, we all know the second iodine is given under safe light. You can't really see the final coating, right? But these photographs that I've been showing you were taken after the plate was developed with mercury, so you can actually see the final coating. So whether you go short with first iodine and then the right amount of bromine and then long with second iodine, if you get to this final presentation color, I think you're going to have a similar effect. in brightest and lightest. So if you find you're coating your plates and you're getting up to this color in first iodine, don't give it long second iodine to take it into blue. Keep it short. So returning to the fogging, I thought, well, that was interesting. The mercury development is giving me fogging on a very, very thin coating. How does that work with Becquerel? So I thought I would just go down that road. So what I have done here is I've made iodine-only plates with 4 levels of iodine on it, going from light yellow to full blue. The set on the left is printed out with a yellow glass filter. The set on the right is printed out with a red glass filter. Information I gleaned from this is that now the thin coatings, they're not fogging, so the fogging effect is due to the mercury. But what I have learned, and what is interesting, is if you look at the yellow glass filter, this daguerreotype plate is sensitive to yellow light. It's fogging with a 90-minute printout exposure. So these are just scans of the colors of glass. Just went to a stained glass shop, picked out a piece of yellow glass, picked out a piece of red glass. You can actually get the spectral transmission curves from them. And so these are the spectral transmission curves that I've gleaned from the 2 pieces of glass. You notice that the yellow glass passes light from the 470 to 600 nanometer range, whereas the red doesn't start to pass light until the 600 nanometer range. So again, looking at the coating and then seeing where the fogging is, it's a clue that the daguerreotypes can see yellow light. It just takes a lot of time. So the next thing I want to talk about is the color of blue studio glass. So on page 30 of Daguerre's manual, Arago gives a report. And then at the bottom of page 30, we can see written, Mr. Daguerre has found that the silver iodide sensitivity is unaffected when the light is made to pass through certain blue glasses. By placing one of these blue glasses between the person whose portrait is to be taken and the sun, the image will be obtained almost as quickly as if there were no glass. Moreover, the light being very soft, there will be no fear of distortion of the features. What's he saying? He's saying with a very dark blue glass, you can put that between the light source and the sitter and still get the same photographic effect, but it won't be so harmful to the sitter's eyes. You won't get the distorted, squinty, look in the sun for very long and you're going to be squinting. Daguerre knew this because he was working with colored glasses with his diorama and mixed pigments and phosphorus. And even before Daguerre's manual, it's written in a letter by B.O. to Fox Talbot that Mr. Daguerre had found some lenses of a very beautiful dark blue, which reduced the light greatly, and when they were interposed, they did not weaken the effect on its substance any more than a white, perfectly translucent lens would have. I've never seen a blue camera lens, nor I don't even really see a reason why you'd want a blue camera lens. The real important thing here is in the early days of studio lighting. So here we have a daguerreotype by Robert Cornelius in May of 1840, Philadelphia. And you can pretty much see that he's taking Daguerre's advice verbatim. The way he has his studio lit is he has 2 mirrors hanging out the top floor window. The sun is bouncing off one mirror onto the other mirror, and then before it blinds the sitter, it passes through a glass aquarium right there. And the glass aquarium is filled with copper sulfate solution. So copper sulfate solution was really the very first photo filter. An interesting idea, and it could still be of use to anyone here making daguerreotypes with electronic flash. I have to thank Curtis Werfritz, who made that observation this morning when I shared this slide with him. That, Jerry Spagnoli, if you look at all of the Chuck Close images, you can see the 6 heads, 6 bare bulb heads reflected in the eyes. it's a physical assault on the sitter. That 36,000 watt-seconds of light go off. The sitter covers her eyes. I'm blind! And then they do it again. So if Jerry went to the stained glass shop and bought some very, 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 very dark blue glass and put it over each one of his heads, they wouldn't even feel the light. Anyway, just a thought. Just a thought. A year later, Richard Beard in London sets up one of the first portrait studios at the top of the Royal Polytechnic. The entire studio roof is quarter-inch thick blue glass using the Walcott reflecting camera, and the cameras were actually on a track and they could rotate around the room as the sun rotates around the sky, and the sitter would rotate around. Like this one. Interesting thing is the roof is constructed of blue glass and the studio is contrived to revolve the sun. Exposure taking about 5 seconds. This would indicate that bromine is used in conjunction with the Walcott camera. In a few minutes the process is complete and a faithful likeness is presented to the sitter. So, just to drive this point home one point further, Antoine Claudet, phenomenal Daguerrean practitioner, experimenter, writer, and scientist. In his booth at the Great Exhibition of the Works of Industry of All Nations, otherwise known as the Crystal Palace Exhibition of 1851, he shows an experiment that I've replicated here. This is Claudet's photogenic paradox. And so what Claudet did was he took a piece of very dark blue glass, and behind the glass he put a lithograph of Prince Albert. And then he took a piece of very clear yellow glass, and behind it put a lithograph of Queen Victoria. And when he made the daguerreotype, that's the result. It's like the daguerreotype doesn't have any problem with blue glass, no matter how dark it is. And this can be explained if you look at the transmission curve for it. The blue glass passes 90% of the actinic light through to the plate. It might as well be clear glass to the daguerreotype. Now the yellow glass blocks pretty much all of the beneficial light to the plate, which is why we can't see Queen Victoria at all. Other Daguerreans working with the spectral response of the process, John Draper, he was working with silver salts on paper back in the 30s. But as soon as the daguerreotype process came out, he became very much interested in what the process could teach him. So this is a daguerreotype plate made sometime between 1840 and 1844. I know it has a later mat on it, but it's an early plate. And it's the spectrum through a glass prism on a plate, which is fine for a scientist. But for me, I really want to know how the daguerreotype works in practice. So I devised my own reflective target. This is a 16 panel Pantone color swatch and grayscales around it. And it's taught me a lot using this target. The daguerreotype that results from this one looks something like that. And if I overlay the target colors, you can really start to get a sense of what colors the daguerreotype plate really sees well. You can see green might as well be black, pretty close to black, depending on the green. Reds, yellows, same thing. But what's really interesting is just that color just a little bit off green or just a little bit off red. So when you get into the magenta or the red magenta or the cyan, green cyan, you can be fooled when you're making a daguerreotype thinking, oh, that's red, it's going to photograph quite dark. And you get the plate off the bath, think, oh my gosh, that's lots of good tone there. So the particular color is very, very important in how the plate's going to respond to it. So if you plot the reflection percentages of the particular colors and you compare the images and see where the tones lie, in this graph, when I compare the target versus the daguerreotype result, tells me that, you know, without the working range in normal practice is just a little bit beyond from UV to 415 nanometers or so. So you have to understand that if you're a curator, if you're a photographer, if you're educating people, or else very strange things start to happen as soon as we get further away from our understanding of process, the more chance there are to misread an image. So this is a daguerreotype in the George Eastman House collection. The descriptive title is Portrait of a Blind Man Holding a Cat. And if you read the Taschen book, the curator has written this: trust was also surely a factor in another portrait sitting which resulted in a striking portrait of a blind man holding his cat. Unable to experience the daguerreotype magic for himself, the subject nevertheless understood the importance of having his likeness made and relied fully on the photographer to make a faithful and sympathetic portrayal. That's a very heavy statement. However, there's another alternative. I talked to an eyeglass expert, antique eyeglass expert via email. His name is Ed Welch, and he wrote back, if you notice that these have 4 lenses on them. There are 2 regular at the front and 2 that open to the side to shield light from the eyes from light. The reason for the shading the eye is that people with syphilis were bothered by intense light. Dr. Richardson patented this particular spectacle design as a therapy for a condition known as iritis, which is a side effect of syphilis, which gets painful reaction to bright light. Where are you going to find bright light? Probably in a daguerreotypist studio. Whether these lenses are green or not, it's open for debate.
So I designed an experiment to see if I could determine what color lenses the man with the cat may have been wearing. And so here I have a picture of my daughter's eye, over which I've placed 3 different levels of yellow filtration, some green filtration on the right, clear glass in the center, orange above it, and blue below in the center. And here's the digital version of the target and the daguerreotype that resulted. We can see the medium green photographs darker than we see in the daguerreotype, and a medium yellow photographs just about the same as we see in that image. When we look at the image closely, we can see that the man's eye is barely discernible in the daguerreotype, and he is looking directly into the lens. So I would say that the color of the lens would be somewhat between the medium and light yellow or medium and light green colors.
And just to drive it home one more time, I did a photograph of my friend Sid wearing those types of glasses, and you can see the curve of the transmission curve of the glasses, and you can see she's as well sighted as all of us. Now I want to talk about the colors the process gives back. And we talked about the colors of iodine, we talked about the colors the plate sees, now I want to talk about the colors the plate gives you. This daguerreotype I made in Pittsburgh. It's the Andy Warhol Bridge. It's taken on the most miserable, dismal day. There's no way in Earth that these are the colors of nature. There's yellows, there's blues, there's magentas, lovely sky tones. This is literally a gift from Daguerre. This image was exhibited at the Young America show in 3 venues, and I talked about this in 2005 when I gave my lecture on Southern Hawes. And the thing about this fellow here is, depending on if you dip your knees just slightly or stand up, he'll switch from cyan to warm to cyan. The term for that, as I understand it, is called prismatic effect. As the plate is held in hand and you turn it slightly, it'll flip. You get this flip. And I was really interested in what is the cause of that phenomena. Not every daguerreotype will do that. A lot of Southern Hawes tend to. And that's part of the magic of the process for me, and I like to try and pursue that kind of aesthetic in my work. So I did this experiment. This is replicating Baron Groves. On a single plate, you can put 9 different combinations of iodine and bromine on the plate. And so I have iodine in 3 levels going up and down, and then bromine in 3 levels going across, making a daguerreotype of my test target. And I noticed in particular 2 of the patches, if you will. The upper left one was given 50 seconds iodine and 75 seconds bromine. The center plate was given 100 seconds iodine and 50 seconds bromine. Both good images. Both would work fine. But I noticed that the center plate had really strong prismatic effect, but the upper left plate, not so much. And I thought, well, I want to look at these more closely. Because I want to see if there's any way I can determine if this prismatic effect is due to image particles. So the 11 steps on the wedge, I went into the scanning electron microscope and we looked at them at 20,000 times. So what I have here is, on the left of the left pair is the upper right piece. On the right of the left pair is the center piece of the plate. And they were taken with a scanning electron microscope, and next to it is the colors images from the scanner, from the Epson scanner. So you can actually compare the image particles and the colors. The pair on the right are the same 2 plates photographed with a Nikon D3 when the plate tilted 25 degrees to try and capture the shift. So you may or may not be able to get an idea. If you look at the 2 right plates, you can see the color, how much the color shifts, and if you look at the 2 left, you can see how much color shifts. Anyway, so I thought, well, I can see it, but I want to see if the scanning electron microscope will actually help me explain it. And at the end of the day, the result is not really so much that the particle size and shape change at all. It's just really, this is a shift in photographic speed by about a stop. So the frequency, the size, a certain number of particles of a certain number of size on a plate will give you a pink look. When those particles become more frequent, the color tone will shift again. It's probably getting a little bit beyond what even I understand. So I'm going to move on. So the final thing I want to talk about is the color of development. So this is a daguerreotype. What I've done is I've taken a single shot of 4 targets. So the plate's sensitized to a uniform iodine, bromine, second iodine, exposed for a certain amount of time. Then I masked the subject and left a perimeter, fancy matte perimeter. And I gave an additional exposure which I knew would be intentionally grossly overexposed. 3 stops more than what would hold as a white. So I wanted to really, really give a lot of exposure to the perimeter. And then, in development, I masked the developers. So the one quadrant got 1 minute development, the next quadrant got 2 minutes development. The next quadrant got 4 minutes development, and the next quadrant got 8 minutes development. So with the same exposure, you can see how development can control things such as solarization in the sky and photographic speed. So you can gain more speed as you push the development, and the tones shift. So if we look at them again under the scanning electron microscope, you can learn a lot. And I'll just kind of say that when you use a scanning electron microscope, you can actually analyze the average particle size. You can pick 10 spots and it'll come up with the math for you. And so in the 1 minute development, if you look at the lower left square, 1 minute development, the average particle size is about 230 nanometers. And if we just skip the middle two and go to the 8 minute development, the average particle size increases to 330 nanometers. So from 230 to 330, particle size to go from blue to a very bright white. The other thing you notice is not only have the particles gotten bigger, but there's more of them. As you extend the development, more particles come onto the playing field. So it's particle size and its frequency, which is what's going to give you these colors. So as you see these pinks and these greens and these cyans, these lovely prismatic effects, it all has to do with a careful control of particle size and frequency. So to conclude, what can we do with all this information? What I have on screen here are two daguerreotypes made on the same day at Peters Valley's workshop. The one on the left is one of my students. The one on the right is mine. Same day, exactly the same sensitizing, exactly the same camera, exactly the same subject. And you'll notice, we talked about what the plate sees. It doesn't see green so well, it sees blue very well. So if you look on the plate on the left, the sky is solarized with extra exposure. And the details in the grass and the foliage is a little darker than seen in life, a little dark. So the plate on the right, same coating, same exposure, not same exposure, but same coating, same subject, full detail in the grass, full detail in the tree trunks, and holding back the solarization. And how this was done, this is the only trick I'm going to show you today, is the 86 method, I'll call it. And simply put, the 86 method is if you take a number 8 Kodak Raton filter, which is a yellow filter, put it over the lens. Now we know from Queen Victoria that the daguerreotype doesn't see it. However, with 6 more stops exposure, you'll get that. The plate, I learned from the Becquerel experiment, the plate does respond to yellow. Right? It's a 90-minute printout. Right? But so with a yellow filter, a number 8 filter over the lens, and 6 more stops, you'll eliminate all of the really active actinic, ultraviolet, blue, violet light. Just deal with the yellow light and just give enough exposure on the plate to record the scene. And you can you can take control of the process rather than have the process take control of you. Thank you.
Thanks very much, Mike.
Okay.
That was stellar stuff. And that concludes the Image Object Symposium. Thanks for coming.
Thank you, Alan.